Hi guys, welcome to part 2 of all you need to know about logic gates to fix stuff. In part 1 I discussed the theory of logic gates, how they basically operate, truth tables and such like, and if that doesn't mean a great deal to you, I suggest that before you watch this video you watch part 1 and I will link it in the description to this video. So hopefully you've all watched that, yeah? So in part 2 we're going to do some practical experiments. So on this piece of Vero board I've built all the basic types of logic gate, and we're going to look at the operation, we're going to measure some voltages. But just before we start I want to refer to a video I found on YouTube which has about 1 million views talking about these types of circuits, and the guy, I have to say, got it wrong. So I just want to show you what this guy was saying, because it's been viewed so many times. A lot of you may have seen this video, and I will just prove what was wrong, and I will show you that it was wrong, and I will show you the correct way to make these circuits. Okay, so the first circuit we're going to talk about is the buffer. This is the documentation from part 1 of the video, and you can see that a buffer circuit, basically when the input is high the output will be high, when the input is low the output will be low. The circuits I've built use a 5 volt supply, so high is represented by the presence of 5 volts and low is 0 volts. Okay, in real life logic circuits they may use different voltages. Common ones are 5 volts, 3.3 volts, 1.8 volts and sometimes lower, but we're using the 5 volt circuit to show these examples. Now let me just show you the other video I found and explain why it was wrong. Here is the video I'm referring to. This has in 1 year almost 1 million views, but in fact the information given in this video is incorrect. I'll just play a couple minutes of it, you'll see what the guy is saying, and then I'll explain why it is wrong, and I will show you by building the circuit he is demonstrating what the problem is. Okay, so let's just listen in for a moment.
Same. So if we were to make a truth table with the input and the output, if the input is on, which means it has a binary number of 1, the output will also be in the on state. If the input is in the off state, which means it has a binary of 0, the output will have the same binary number of 0 as well. Now let's draw a circuit to represent this. And the principal element of this circuit will be an NPN transistor. This is the base, this is the collector, and this is the emitter. Now we're going to connect this to a power source, and we're also going to use a light emitting diode. Now the light emitting diode, it's going to represent the output of the circuit. Now let's connect this to a voltage source. So here is the input, which we'll call it input A. And what's going to happen if we apply a voltage to point A? So if the input is in an on state, will the LED, will it be on or off? Well, once you apply a voltage to the base, the transistor will turn on. Current will flow from the collector to the emitter. Therefore, the LED will be in an on state. So this corresponds to a 1 for the input and the output. Okay,
so this is the circuit. There's a couple things. First of all, he's omitted the base resistor. In actual fact, what would happen is it would just burn the transistor, but that's not actually relevant to this discussion. Okay, what is relevant is this. So he's saying that when you put a voltage on here, a 1, you get a voltage on the output here. In actual fact, you don't. What he has drawn here is not a buffer but an inverter. So let's have a look at the circuit. I've actually made one. Let's get the voltmeter and let's just prove that is actually the case. This is the actual circuit you just saw in that video. So we have 12 volts on here. This is ground here. These little probes here are actually connected to 5 volts, so I can inject voltage into the circuit. We have a 120 ohm resistor connecting to the anode of our LED here. The cathode connects to the collector of the transistor, and the emitter of the transistor is connecting to ground. So when we switch this transistor on, the LED will turn on. This is the base resistor. I mentioned that he omitted, but it really isn't relevant to the discussion. In fact, if he used MOSFETs, you wouldn't even need it. But he did use a bipolar transistor, so I think I should mention it, okay? So let's put some power on this. This runs at 5 volts, and let's have a look to see how the circuit actually operates. Power is on. So at the moment the LED is off. If I take 5 volts now and connect it to the resistor, like so, the LED comes on. So that is doing what he said, but electrically it is not operating as a buffer. Let me show you. I have the voltmeter, so let's have a look at some of the voltages in our circuit. On the anode of the LED we have 5.12 volts, okay? And on the cathode we have 4.3 volts, yeah? That also appears on the collector of our transistor. Look at the base. Actually reads a negative voltage. I'll explain why in a moment. And the emitter reads 0. Okay, so that's with the LED off. Let's put that onto a piece of paper. Here is the circuit then. Resistor, LED, collector, emitter, base, and a 1K resistor. And the voltage I'm measuring with no input. On here, 5.1 volts, which is the supply voltage. On this end of the LED, we also have 5.1 volts. Okay. On this end of the LED we have 4.27 volts, and on the base we have minus 2.8 volts. Now these voltages look a bit odd, yeah, and you probably want to know why are they a bit odd. Well, the reason we see 5.1 volts at both ends of the resistor is because no current is flowing, the transistor is switched off. And if there's no current flowing through the resistor, there can be no voltage drop across it. So that's 5.1. So why do we see 4.27 volts here? Well, the reason actually is this. When we're measuring on the 120 ohm resistor, there, before the LED, our test meter is connected to ground, and it's connected to here. Okay, and our test meter, in order to measure the voltage, must pass some current. If there's no current flowing into the test meter, then it can't measure any voltage. Yeah, there has to be current flowing for it to be able to see there's anything there, yeah, to give a reading. Now, the resistance of our multimeter, what's called the input impedance, okay, is very high, maybe 10 mega ohms. So what we actually have when we connect our test meter here basically is this. We have a circuit, 120 ohms, 10 mega ohms to ground. And this is a voltage divider. Now, there's a formula for working out what the voltage here would be. But basically, because this resistor is a very low value in comparison to this one, yeah, it's a very low value in comparison to it, the voltage here will be practically the same as the voltage there. So when I said there was no current flowing, technically, yes, there is a bit of current flowing because it has to flow through the meter. But the current is so small that the voltage drop across a small resistor is zero. That's why we see the same voltage both sides of the resistor. So why do we see 4.27 volts here? Well, the same reason applies. So you have your 120 ohm resistor. Okay, you have your LED. Okay, and then from here, the transistor is off, so we can ignore that. But I'm connecting my test meter from here to ground. So basically, my test meter, which is 10 mega ohms, completes the circuit. Yeah? And some current flows. Now, a diode junction will have a voltage drop. For a normal rectifier diode, silicon rectifier, that's about 0.6 of a volt. That's what you read when you read the voltage across a diode in diode mode, about 0.6. If you've ever measured the voltage across an LED in diode mode, you'll see it reads higher. And the actual voltage drop will vary on the different coloured LEDs and even to different manufacturers of LEDs. But the main factor is the colour, okay? So if we use diode mode, we measure across our LED, you'll see we get about 1.7 volts. But that voltage will vary depending on the current that flows through the LED. It may even be enough off my test meter to just about light the LED up. Yeah, it's lighting up but dimly, okay? So you can see that the LED has a voltage drop of about 1.27. So that's what we're seeing here. We actually have a voltage drop that is more like about 0.8 of a volt, just over 0.87 of a volt. And that's because the LED is passing current, not enough to light it up, and what we're actually measuring is the voltage drop across the LED, and that's why our test meter, our 10 meg load, reads that voltage. Okay, so that's that, and that I think is fairly easy to explain. What is more complicated is why do we see minus 2.8 volts here? Well, the same thing applies when we connect our test meter from here to ground. It's like connecting a 10 meg resistor. And we actually have a current path now, okay, from the collector base to here. And you know yourself, if you test diode junction transistors in diode mode, inside the transistor is effectively diode junctions, okay, two diode junctions. So what we're actually getting here is a little bit interesting. Yeah? The diode junction inside the transistor is actually acting as a rectifier. It's passing current in one direction. And because of all the stray circuit tracks on here, and because the base is at a very high impedance to ground, about 10 meg, the base effectively floats. And what we're actually seeing is stray RF frequencies, mains frequencies, radio frequencies, all the sort of stuff that's floating around in the ether is being picked up by the circuit traces on the Vero board, is being rectified by the diode in here, and the meter is reading as a voltage. That's why we see minus 2.8 volts on the base when we have no negative supply. Where's it coming from? Out of the ether, rectified by the diode in the transistor. So this leads to a couple of things now. First of all, when you have nothing connected to the base of the transistor isn't actually off. Yeah, it isn't exactly off. It's floating, the base is floating. And in fact, if we can put some sort of interference into here, we can probably get it to light the LED. That's the first thing, yeah? To make this circuit actually switch off, we need to connect this end of the resistor to ground, or through another resistor to ground. Yeah? Now I'll show that on our actual circuit again. As I was mentioning, the voltage on the base is effectively floating, and this is why I'm getting some strange readings. And you may also notice that when I touch the end of the resistor, the LED is actually lighting up. Yeah, that's because there's enough leakage voltage flowing through my meter to cause a little bit of base current to flow for it to light up. If I go to the other end of the resistor, it might do it even more so. It's actually about the same. You don't really see any difference in the brightness, but it's doing the same thing. Okay. So to stop it doing that, you need to turn the transistor off. And the way you would turn it off is by connecting another resistor from the base to ground. So down here we have a 10k resistor. Typically this resistor will be 10 times or more the value of the input resistor. Okay, so let's do it. Connect onto here, and I'm going to connect this resistor to ground from the base of the transistor. Okay, so we now have that. If we now measure the voltage on the base, we will see that it's 0. There's no input, it's 0 volts on the base. Okay, if you look now on our LED, it's still dropping the voltage across it as we expect, because this is like a 10 meg resistor. Okay, but if I touch the resistor now, it doesn't turn the LED on. So there's one important thing. Off means connected effectively via resistance to ground to turn the transistor off. It doesn't mean no voltage present on the base, as in not connected to anything. But that isn't why this guy got the circuit wrong. This is just another important thing. Let's turn the circuit on. So we will connect from 5 volts with this little test probe to the resistor. Okay, let's turn it on. I now have 5 volts connected to the base resistor. The transistor is now on. So do we have a logic 1 on the output? Let's have a look. So this is the 5 volts coming in. We know this is 5 volts. This is connected to 5 volts. It's actually connected to this wire. So we still have 5 volts coming in. The anode of our LED is now at 2 volts. Okay, so we now have 2.05 volts. I'll just make a note of it. The other end of the LED connected to the collector of the transistor is basically 0 volts, 0.03 volts. Okay, so I'll make a note of that. And of course ground, the emitter is still ground. Okay, let's have a look at that on our circuit diagram now. So here is our circuit. I drew that wrong, I'll now draw it right. Actually it would work either way, to be quite honest, but I will draw it correctly. There we have it. And let's put the voltages on again. So when the input is 0, and we know it's 0 because this resistor is holding the base to 0, it's clamping it down. This is called a pull down resistor, pull down, yeah. And we also have pull ups, as we'll talk about a bit later. when we have the pull down resistor in holding this to ground, we know because we measured it there is 0 volts on the base. Okay, the voltage on the LED here is around about 4.27 for the reasons I explained. With measuring from here to ground is effectively a 10 meg resistor, and the voltage on the emitter is 0. And this is the output of our circuit. In, out. Okay, so that's what we have when the transistor is switched off. Now let's look at what we have when the transistor is switched on. So when the transistor is switched on, we have 5 volts on here. Okay, I didn't measure the voltage on the base, so I better go and measure it. But what I did do is measure the voltage on the output here, this side of the LED, and it was 0.03 volts. Okay, so the truth table for this circuit in actual fact, in, out, when in is 0, out is high, yeah, 4.27 volts. In fact, we'll call it in is low, it's the same thing as 0, it's low, and out is high. Okay, and when in is high, 5 volts, out is low, 0.03 volts. So what this guy has got a million people to believe is a buffer is an inverter. Yeah, it's an inverter. We can see what it's doing. It's inverting the voltages. High gives you low and low gives you high, regardless of what the LED is doing. This raises another factor as well, something very interesting to understand with electronics. There's 2 ways to turn something like an LED on. One is to put 5 volts on one end of it through a resistor when the other one's connected to ground. And the other is to put ground on one end of it when the other end is connected to 5 volts via resistor. So that didn't come out very well, did it? So what I'm trying to explain is this, and I did get interrupted before somebody called in, but let's just do it again. If we put a switch here, which could be a transistor, okay, could be a switch, we can turn this LED on by connecting this end to 5 volts. It makes the circuit. And you can switch the LED by switching the 5 volts. Okay. You can also perfectly validly make a circuit like this with a switch here, 5 volts. And now we can turn the LED on by switching this end of it to ground. So instead of switching the 5 volts is always present, and we switch it on by switching this end to ground. This is very common, and what you need to remember from this is there's more than one way to turn on an LED. Yeah? Basically, you can turn an LED on by putting a logic 1 on here, a high voltage, or you can turn the LED on by putting a logic 0 or a low voltage on this end. So to turn an LED on, it can be done either way, by providing a high or a low. Okay, that is something, once you completely understand that, you remember that, you will find this very useful in repairing lots and lots of things. The one voltage I didn't measure actually is quite important, and that's the base voltage when the circuit is switched on. So let's have a look at that now. This is where I'm putting the 5 volts into the 1k resistor, so 5 volts. What's on the base? Is it 5 volts? No, it's about 0.75 volts. So let's put that on our circuit diagram and explain why we have this voltage. Here we are once again. When we have 5 volts on the in, then we know, because we just measured it, on the base we have 0.75 volts. The reason that happens is because this basically is a diode junction, as I'm explaining, and the diode junction will have a forward voltage drop, which is in the sort of region 0.5 to 0.7 volts. So this resistor effectively drops the voltage at the base to a level which the transistor can withstand. Okay, if you put 5 volts on here, you would just burn out the transistor. It can't possibly have more than about 0.7 of a volt on it. So that's why we actually see that. Now that only applies to transistors, bipolar transistors. MOSFETs, you can actually apply the full voltage to the gate, and one of the examples I have built uses MOSFETs, so we can see that. Now let's go back to that video we were looking at with the 1 million views on it, in which he explains how to build a NOT gate. Let's see if he gets this one right or wrong.
Now what about if the input is off? So in this case we have a 0 at the input. If there's no voltage at the base, then the transistor will be off. No current will be able to flow from the collector to the emitter. So therefore, the LED will be off as well. So in this case, we have in an on state. So this corresponds to a 1 for the input and the output. Now what about if the input is off?
So now let him just compound his
So in this
error.
case we have 0 at the input.
0 on the input.
If there's no
0
voltage
volts.
at the base, then the transistor will be off. No current will be able to flow from the collector to the emitter. So therefore, the LED will be off as well. And so that's basically the buffer logic gate.
But it isn't, guys, because when the transistor is off, as we've just seen, the collector voltage will be high. We just now have 5 volts or thereabouts on both ends of the LED. Actually, we see the diode voltage drop. So when the input is off, the output is high. Yeah, so this is wrong. Let's see how he messes up the NOT gate now.
So if you have a 1 in the input, you're going to have a 1 in the output. If you have a 0 in the input, you have a 0 in the output. Now the next type of logic gate that we're going to talk about is the NOT gate. So here is the electrical symbol for it. It looks like a buffer gate, but it has like a circle in the front. Now let's call the input A. The output will be the complementary of A. You can also write it as A bar. Now let's write a truth table. So we're going to have the input and the output. So if we have a 0 at the input, the output will be a 1. And if we have a 1 at the input, the output will be 0. It's always going to be the output.
So that's what the previous circuit was actually doing, which he called a buffer. Yeah, we've just proved that.
Opposite. So basically, if the input is in an off state, the output will be in an on state, and vice versa.
So this is like we were saying, with 0 volts on the input, the base, there will be 1 volt on the output. Yeah, that's what we just had. It wasn't a buffer.
Now, how can we represent this using a transistor circuit? The circuit is going to be very similar to what we drew before, but there's going to be one key difference, and that is the location of the LED. So here is our voltage source, and on the left we have our input A. The emitter is attached to the ground, but the LED will be connected across the collector of the transistor and the emitter.
Interesting way to connect to the LED, yeah?
So once again, this will be our output. So let's say if the circuit, or rather input A, is in the on state. Will the LED be in the on state or the off state? Well, let's analyze it. So once we apply a voltage to the base of the transistor, current will be able to flow from the collector to the emitter. So current will flow from the positive 5 volts through the resistor. Now, once it gets to this point, it has two options. The current can flow to the right, or it can flow to the left. Now, electricity will will always take the path of least resistance. And if the transistor is on, then the path of least resistance is from the collector to the emitter. So therefore, no current will flow in this direction.
Correct.
So this will be in the off state because the current has been diverted through the transistor.
Yeah, okay, so when there's a voltage on the base, the LED is off. And in actual fact, what it actually has here is a NOT gate, because with voltage on here, the voltage here is basically 0, and with no voltage on here, the voltage here is basically 5 volts. So he's actually describing a NOT gate with a NOT gate, but this is actually the same circuit he used for the buffer. Okay, let's test the circuit itself now.
So notice that we have a complementary situation. The input is on, but the output is off. Likewise, the reverse is true. So let's say that the input is off. There's no voltage applied at input A. So what's going to happen? Current will still flow through the resistor. Now, once it reaches this point, because the transistor is off, it cannot flow through the transistor. So therefore, it has no choice but to flow through the LED. So therefore, the LED is in an on state. So as we can see here, if we have a 0 at A, the output will be a 1. And if we have a 1 at A, the output is a 0.
Okay, so there you have it, guys. Let's actually make some measurements on this circuit, because I've built the circuit. Let's see what we find. And here is the circuit he was just describing. So we have this one. Okay, I'll just draw around it so we know what in fact we are looking at. We're looking at this circuit. We have then a resistor 120 ohm connecting to 5 volts. This end of it goes to the collector of the transistor and the LED. The LED and the emitter of the transistor go to ground, and we have a resistor connected to the base. So with no input on the base, let's make some measurements. So we have five volts on here. The other end of the resistor is actually 2 volts. Okay, it's 2 volts. The base of the transistor is reading minus 2.1, and that's because it's floating. So let's fix that problem first. Let's connect our 10k resistor from the base to ground. Okay, I've done that. It's still, the LED is on, and now on the base we have 0. Other end of the resistor we have 0. This, as I say, was 2 volts. So let's put these on a diagram of the circuit. This is the circuit the guy built on his video, or described rather than built. I think if he built these he would have realised they were wrong, but we'll see. Maybe he wouldn't have done. Again, he omitted the base resistor, but it's not really relevant. He omitted the pull down resistor, but it's not really relevant, apart from the circuit won't work properly without it. And he connected from here to here, an LED. So now, with 0 volts on the input, we have 5 volt supply, and here, which is the output of the circuit, we have 2 volts. Okay, that's what we actually have. We have 2 volts on there. Let's now turn our transistor on and let's see what we get. To turn the transistor on is quite simple. We put 5 volts onto the base resistor. Okay. And now it's gone off. And something actually smelt like it's burning. And that's because I made a mistake in this part of the circuit. Let's have a look. So, on our base resistor, we have 4.7 volts. What's on the base? 4.7 volts. What's on the emitter? Ground. And the reason we have that smell of something burning is because there's an error in the circuit. Okay. And the error in this case, if we look, is that the base resistor, I forgot to cut the track. So we now have on the base of our transistor about 4 volts and the emitter is 0. And as I mentioned earlier in passing, and I didn't plan this by the way, it's just as it happened, but it will prove some interesting things. If I measure 5 volts in fact on the base, 0 volts on the emitter, 4.3 volts on the collector. So we have more than 0.7 volts across our transistor base emitter. Let's fix the problem. Let's actually cut that track which I forgot to cut. Okay, I've cut the track now and we can prove that the track is cut. Let's move some of these out of the way a little bit. We can prove the track is cut by measuring the resistance on the 1k resistor. Does it still have a short across it? No, it reads 1k. So will our circuit actually work now? Well, the first thing we see is that the LED is no longer on. It's not lit up anymore. Let's look at some of the voltages in our circuit. So with no voltage on the base, I've disconnected the 5 volts. We go to volts range. This is now reading 0, okay, as you'd expect. We go on to the actual base of the transistor. It's reading 0. Collector is reading 5 volts. And the emitter is 0. So if we have 5 volts on here, why is the LED not lit up? One end of the LED has 5 volts on it. The other end has 0 on it. Yet it's not passing any current. Let's put 5 volts on the resistor now, feeds the base of our transistor. So we now have 5 volts on the base of our transistor. What voltages do we see? So there's 5 volts coming in. There's 1.5 volts now on here. There's 2.2 volts on the base. And there is nothing on the emitter. So there's two things here. One is we have too much voltage on the base of the transistor, and the only way you can have more than 0.6.7 volts on the base emitter of an NPN transistor is if the transistor is open circuit. Yeah, simple as that really. So let's take this transistor out, and it should, I would imagine, read open circuit base emitter. Well, it actually says it's an NPN Darlington transistor. So in some ways it is still working. It's not open circuit on the base emitter, but it's like it has some extra resistance in the base emitter. Let's try it in diode mode on the meter. Okay, so let's have a look on here. So Base is in the middle. .6. So it read to the other one. 0.6. And across the collector emitter. Well, it actually reads okay on the test meter. Let's get a good one and compare it with this one again on the analyzer. And what you might notice, by the way, is that it's saying the voltage base emitter is 0.94 of a volt. That's why it's saying it's a Darlington transistor. Well, that reads like an NPN transistor. Okay, and the voltage base emitter 0.74, which is what we were reading on the good one. So it's definitely damaged it, although it hasn't actually gone open circuit. While we're at it, let's see what happened to our LED. So I can probably test this in circuit actually now I've removed the transistor. Let's have a look. Okay. Well, the LED doesn't light up, unknown faulty components. So there seems to be a problem with the LED. So let's remove that. Here is the LED then, unsoldered. Let's see what the component analyzer says on it now. No component detected. So the LED actually went open circuit. Let's have a look why that could have happened on paper. Here is our circuit then, and basically the error I made was that there was a short circuit across the resistor from here to here. So the 5 volts went straight into the transistor. Now a transistor internally, effectively if you like, is like 2 diodes. Okay, collector, emitter, base. Although you can't actually make a transistor using 2 diodes like that. Remember the one with the open circuit base with the -2 volts on it? This effectively diode was acting like a rectifier and just picking up stray noise. And the reason we got a negative voltage is because it's the anode is here. So effectively negative voltage flows that way, positive voltage flows that way. That's why we got minus something. Until we added the resistor to ground and stopped the nonsense, yeah? But in our case, what we've done is this. That goes to ground, yeah? We put 5 volts on here with no resistor to limit the current. We have a resistor up to 5 volts here and here to ground. We have the LED. So where's the 5 volts going to go? Straight through that diode, forward biased, straight through the LED, nothing to limit the current, bye bye LED. And it didn't do the transistor a lot of good either. That's why the LED blew. A Darlington transistor is actually 2 transistors in one package. So what we have is this. Arrangement, and usually like that. So effectively this transistor drives the base of this one, and the gain of the Darlington pair, although this will be in one package with 3 legs, the gain is the gain of this transistor multiplied by this one. So if this has a gain of 100 and this has a gain of 100, the total gain is 10,000. And that's what a Darlington transistor is. Now between the base and the emitter, you'll see you're going through 2 diode junctions, and this one is about 0.6 of a volt, for example, and this is about 0.6 of a volt. So if you measure on the Darlington from here to here, you'll see roughly double that, about 1 volt, or maybe a bit more. And that's what was happening with our faulty transistor. The voltage drop across the base emitter had gone much higher than it should be, which is why our analyzer thought it was a Darlington transistor. This is also something you should be wary of if you use component analyzers. If you ever see it telling you something is a Darlington transistor, do not assume it is a Darlington transistor. Go look up the data sheet. Yeah, if the data sheet says yes, it's a Darlington transistor, and your analyzer says it's a Darlington transistor, that is fine. Yeah, but don't just assume because it tells you that you have a good Darlington transistor as opposed to a bad normal bipolar transistor. I've now repaired our test circuit, so let's put 5 volts onto the resistor here. You can see it switches the LED off, it switches back on again. Let's see what's happening to the voltages now. Okay, so once again, here is our voltmeter. The voltage on the collector now is 0.04, near to 0. Same obviously on this resistor, same place, 5 volts. So the output is now 0.042. Let's put on our diagram as well. Here is the circuit then. So when there is 0 volts on the base, the output is 2 volts. And when there is 5 volts on the base, and this by the way now will be 0.75 like you'd expect it to be, the output is 0.04. So a high on the input is producing a low on the output. Let's put it on the truth table. So we have A is the input, we have Y is the output or out. We put a high on here, we get a low here. When we put a low on here, well, what do we get? We get 2 volts. Well, what's that? It ain't high and it ain't low. Which brings us to another interesting point about logic circuits, especially logic ICs. So we have low, 0 volts, and we have high, the same voltage as supply voltage, 5 volts. But we have all the voltages in between as well. So the output can only ever be high or low. It can't be anything else. The output is either 5 volts or 0 volts, really. So what happens when there's an in-between voltage? Well, basically we have thresholds. So a logic low is considered to be anything that's less than 0.8 volts in 5 volt TTL logic circuits at least. Other chips, 3.3 volt logic and such like, may vary. But anything less than 0.8 is considered to be a low. Anything more than 2.5 is considered to be high. So 3 volts would be high on a 5 volt logic circuit. Anything that's in between these two values is indeterminate. The output isn't stable. It could be either high or low, almost at random. So this truth table for a NOT gate in our circuit that we copy from this other guy doesn't work because that's indeterminate. And the reason it's indeterminate is because it's neither more than 2.5 volts or less than 0.8 volts. Okay, so that's why the guy got it wrong and a million people viewed it. What I find a little bit strange, and I didn't look through all the comments, there's many comments on that video, but I went through so many and I couldn't find a single person who realised it was wrong. So I can only assume now we have a million people out there who don't understand transistor-based logic circuits, and I hope some of those 1 million people are now watching this and can go back and say to the guy, I'm sorry, but you were wrong. Okay, so I won't refer back to that video anymore, but let's now build some proper logic gates. Let's build some proper ones that actually work as they're supposed to, just using transistors, and let's measure the voltages in them. The first circuit this guy tried to build was a buffer, and what he actually built was a NOT gate, which works as a NOT gate, but it isn't a buffer. So let's make a buffer using transistors, okay? So the way we do it is this. We take a transistor, collector, emitter, base, okay? A base resistor, we'll use 1K. We'll put it here because it was less blurred. The resistor to ground so the base doesn't float and do odd indeterminate things. 10K resistor. And then from here, this is the output of our circuit. So this is in, this is out. And we can connect from here, the resistor, an LED to ground. Here is the circuit that I built. And again, I've attached the lead to the 10K resistor to hold the base down to prevent any instability, and we can measure the voltages that we have. We have no input at the moment, so we should have 0 volts on the base. So this is the input, 0 volts, this is the base, 0 volts, and the output going to the LED, this is your output, 0.43. Okay, so we'll just make a note of that one. The collector is 5 volts, it will be because this is the 5 volts coming in. Okay, and the other end of the LED is ground. Okay, let's now put 5 volts on this one, and I'll just make sure I did cut the track. Yes, so we won't be blowing any more of these up. So we put 5 volts on here and the LED should switch on, which it did. Okay, now let's see what we have. So on the input now, we have 5 volts. On the base, 0.75. No, in fact 4.5, and the reason it's 4.5 is because the emitter is not 0. Look, the emitter is now 3.8, and that's the output of our circuit, 3.86. The voltage then comes through the resistor into the LED, probably about 1.7 on this end, 1.9, and then the other end of the LED is ground. So the output of our voltage on the emitter, 3.86. So let's make a note of that. We'll just draw it again so we don't make too many markings and voltages on the same diagram. 10K, 1K. LED, ground, out, in. Okay, so when there's 0 volts on the base, we actually had 0.43 volts on the emitter. Okay, so 0 in gave 0.43 out. The reason we've got a little bit of voltage here again is just leakage current when I effectively connect my meter in circuit. Yeah, there's a little bit of tiny bit of current managing to flow through the transistor. That's why effectively we don't have 0. But as I said, in a logic circuit, anything less than 0.8 volts is considered a 0 on a 5 volt circuit. So in our truth table, in, out, in is 0, which is a low, out is 0.43, which is a low, it's less than 0.8. What happens when we switched it on? Well, when we switched it on, we got 5 volts here. The base Let's have a look to see how to build some more logic circuits using transistors. So the next one I think I will build would be an AND gate. And of course, not being a circuit designer myself, more of a fixer, easiest way to find out how to do that is on the internet or even on YouTube. So yeah, why not? Let's have a look to see what we can find. Here's a video, 7 years old, 2.1 million views, nice big channel. So let's see how we should build an AND gate and then we can test it.
Input is on and the output is off. Pretty straightforward. So let's look at some other logic circuits that we can make with transistors.
I have some serious doubts about this because Luke, this is that circuit we just proved was not an actual gate. Yeah, it was a never gate. Yeah. Oh dear. Let's see.
Okay, this next circuit that we'll look at, we've got two transistors. It's just kind of this left half of the board here. We've got two transistors, and the way it works is we've got these inputs, which again are kind of, I haven't drawn the whole circuit out, but we still have this resistor coming from the positive rail here through the push button switch and then into the base of the transistor. And so that
oh well, that's good. At least he isn't going to blow the transistors up. Let's see if it works.
That allows us to put a current through that transistor. And we've got two of those. And so what happens is that if both transistors are turned on, then that will complete the circuit through this resistor here, and then through this LED, and then through the first transistor, and then over here and through the second transistor. And so if both transistors are turned on, then the LED will turn on. And this.
Hang on a second. If both transistors are on and the LED will turn on, it must be because the LED has a 5 volt supply on one end and 0 volts on the other end. So surely when these are both on, the output, which is here, is low, and that's a NAND gate. Yeah.
This is a little piece of logic that is called an AND gate. And
really?
And this is the truth table for it. This is the symbol that we would use if we were drawing a more complex logic circuit. We would actually, instead of drawing all the little transistors, we would just kind of draw this whole circuit as just an AND gate using this symbol. It's kind of rounded on this side and squared off on this side. And the truth table for it says that if A and B are off, then the output is off, and that's kind of what we have now. So both of these are off. I'm not pushing either one, and the output is off. If B is on and A is off, then the output is also off, and we can test that just by pushing the button and the LED doesn't come on. Same thing, if A is off, if A is on and B is off, then the output is also off. We can test that by pushing the button here. But if both of them are on, then the output is on. And that makes sense. If both of these are on, then that completes the circuit all the way through. And so if I push both the buttons, then you can see the LED comes on because we're completing the circuit all the way through.
Yeah, sure, by putting 0 volts on this end of the LED, because this one is already attached to 5 volts via the resistor anyway. That's constant. Surely this is a NAND gate. Yeah.
So how about this other circuit over here? It's a little bit...
Well, let's look at your other circuit in a minute, but let's build this one first because I am not convinced at all this is actually an AND gate. Let's see what you've built. And here we have the Ben Eater AND gate. I've built it. So exactly as he suggested, or rather described, we have the resistor 120 ohms from 5 volts to the anode of the LED. The cathode of the LED connects to the collector of the first transistor. Let's call this Q1. The base resistor is here. And then we have the emitter of Q1 going to the collector of Q2. Again, the base resistor is here. So we can put our inputs here, A and B. We can have 0 or 5 volts. And then the emitter of this one goes to ground. This is not part of the circuit. These are the 10k resistors I was playing with before to stop the base floating, and I might need to do that again with this circuit, but let's just try it without and let's see if it actually gives the results we're expecting. And I'm expecting this to be a NAND gate, but 2.1 million people have watched that, and I looked through the comments and nobody obviously said this circuit is wrong or doesn't work. So yeah, 2.1 million people can't be wrong, can they? Let's see. I'll switch the circuit on. So at the moment we have 0 on the input. So this is A, there's 0 volts, and this is input B is 0. Okay, well it's reading the -2, that's because it's floating. It doesn't affect the operation, but let's just stop it from doing it by putting the 10k resistor onto the base. In fact, no, actually, let's not do that because I want to prove that this circuit doesn't work. So in actual fact, we have 0 and we have -2.3, but let's just consider them both be 0. Yeah, I'll put the resistor on, I've proven it. So on the output then, Y, we have 5.4 volts. I think my power supply is a little bit more than 5 volts at the moment. Okay, we have 5.47 on the output. So let's make a note of those. So when A and B is 0, basically the output is 5. Let's now put 5 volts onto A. Input A now is 5 volts. We can read it. Input B, well, okay, we know why it is negative, but the transistor is definitely off. And the output is actually reading 6 volts. That's these floating voltages giving some strange readings, but let's make a note of it. Now let's put the 5 volts onto input B instead. Once again, the LED is off, and we have 5 volts on B. Well, yeah, okay, on A. I'll put the 10k resistors in a minute, and the output is actually now 5.5 volts. So we'll make a note of that. And then the last condition is to put 5 volts on both inputs, and the LED comes on. So what do we have now? Well, we have 5 volts on B, and we have 5 volts on A. We have 0.05 on Y. Okay, surely that's a NAND gate. We'll look at the truth table in a minute. I'll just connect these 10k resistors, just get rid of these floating voltages, just see if that has any effect. I've added the resistors in, so let's have a quick look again. So now we have 5 volts on B, 5 volts on A, and basically the same on the output. We can disconnect A. We now have 5, 0, what we'd expect, and 5 volts on the output. We can disconnect B, so they both disconnected. 0, 0, 5 volts on the output. So you can see, actually, connecting the resistors to stop the base from floating doesn't affect the operation of the circuit. It just affects the fact we actually read a proper 0 volts on the base now. Zero. And this will be 0 now. Yeah, so it just makes the 0 become a 0, but it has no effect. So let's look at the truth table for the Ben Eater Amazing AND gate. So these are the voltages I measured on the inputs and the outputs. This is the Ben Eater Amazing AND gate. Yeah, so when A is low, 0 volts, and B is low, 0 volts, Y is high. Okay, A, B, Y. When A is high, B is low, Y is high. Okay. When A is low and B is high, Y is high. And when both A and B are high, Y is low. Surely that is a NAND gate. Not conjecture, just proof, yeah? That's a NAND gate. Let's see what you can do with an OR gate.
So how about this other circuit over here? It's a little bit different. I'll show you the circuit diagram first. And the circuit diagram for this is a little bit different. So we still have 2 transistors, we still have our LED, but they're wired up just a little bit different. So in this case, the transistors are kind of in parallel. And so if either of the transistors is on, then the LED would come on, because we can complete the circuit through this transistor or through this transistor.
This is looking like a NOR gate to me. Let's hope that's what he says it is.
So if we look at the circuit kind of closely here, we can see that from the positive rail, we come through this resistor and then through the LED, and then we can go through this first transistor. So from the the collector here to the emitter, or we can actually kind of come over to this transistor through the collector and out through the emitter. And then so if either of these transistors is on, then the LED will be on. So we can test that out. So if we turn this one on, it comes on. If we turn this one on, it comes on as well.
That's what you'd expect.
So this is something called an OR gate.
Oh no. Oh no. Please no.
Which makes sense. If this or this is on, then the output is on. And so this is the truth table for it. So if both are off, the output is off.
I think we're just going to have to test this circuit, but I'm sure we know what the results are going to be.
Which is what we see here. But if one of them is on, then the output's on. If the other one is on, the output's also on. And also if both of them are on, because then that'll just complete the circuit either way. And of course, either way, current will flow.
What this guy seems to have a problem with comprehending is that an LED doesn't necessarily come on because you've got a logic 1 switching on one end of it. Okay, let's build it. And here is the OR gate as described in that video. So we have the 120 ohm resistor, we have the LED connecting to the 2 transistors, effectively in parallel as he describes them, and the 2 base resistors. So again, we may have to mess around with the 10k resistors holding the stray voltages down, but we do know the last circuit worked either way, whether we did or whether we didn't. It just read some strange voltages if we didn't. Let's try this one. So we'll switch it on. So again, we have A, B, and we have Y as the output. So first of all, we have, we'll call it a 0 on A, and we'll call it a 0 on B. We know why we see that. So A and B are both low. What's on the output? Well, it's high, 5.21. Let's take one of the inputs high. I'll just move the Y where it's a little bit easier to do it. Here we go. So input A is high and the LED comes on. Okay, so what do we have now? A is, well, it's going to be 5 volts because we put 5 volts on it. And B is, we'll call it 0, and the output is 0.03. So we have 5, 0, 0.03. And then we can do the same with, let's do them both, since we have that one already on there. So they're now both high. Okay, so quite clearly we have 5 and 5 on the input, and the output is still 0.03. And then the last one is with input B high and input A low. Again, the LED stays on, and we now have our peculiar 0 volts, but we know why. We have 5 volts and we have 0.03. Let's look at the truth table. Here is the schematic, which is basically the same one that he used. LED connecting to 5 volts. So we have the 2 transistors and the base resistors, inputs A, B and Y, and we can now create a truth table from the voltage we have. So when A and B are both low, output is 5.21 volts, which is high. This is A, B, Y. Should have left a bit more space, never mind, because we know where this is going. Yeah, high, low, output is low, 0.03 volts. Low, high, output is low, the same. High, high, output is low. And that, if we look at our truth tables, is not the truth table for OR gate at all. it is the truth table for a NOR gate. So that's what he built. So I wonder, because he's building all these transistor circuits, how does he go on and build a NOR gate and a NAND gate? Because he already built them and called them something else. Okay, let's see how he does it.
So you can see here we've got two different circuits. They're very similar, but slightly different operation. One is an AND operation, the other is an OR operation. So let's take a look at something.
No, it's a NAND and a NOR, because we've just proved it ourselves.
A little bit more complicated. So this is get a different board here, different circuit, and let me just power this up. So
hang on, what happened to the NAND and NOR gates? You're now on XOR. Okay, maybe it comes later.
This we've got actually 5 transistors in this circuit, and it is basically the same kind of idea here. We've got 2 inputs that we can, in this case, turn on and off with these little push button switches, and we have got an output over here, which is this LED. And what we've built is what's called an exclusive OR gate, or an XOR gate, and it's similar to the OR gate, which is it's off if both A and B are off, and it's on if A or B is on. But what's different is that it's off if A and B are on. And so we can actually kind of see that operation. So right now it's off because neither of them are on. But if we turn on A, the output is on. And if we turn on B, then the output is on. But if we turn on both at the same time, the output goes off. And to kind of understand how that works, I've got the circuit diagram for what's built here. And you can see that...
Oh, this is going to be interesting.
That if we just look at this part over here, it looks a lot like the OR gate. Because we've got the 5-volt source going through...
The OR gate that was a NOR gate, yeah?
Through a resistor, through the LED, and that's what's going on here. So we have a 5-volt source going through the resistor, through the LED, and into either of these transistors. So it can go through either of these transistors. And then the inputs for those transistors are the A and B. So these yellow wires come over here and then jump over to the switches. So if either this or this is on, then that'll complete the circuit, at least through to this point. And so in the OR gate, we just had this connected directly to ground. And so if this or this were on, then that would complete the circuit all the way to ground.
With a NOR gate.
But in this case, in order to get to ground, we've got to turn this transistor on too. Otherwise, we've got a 5 volts sort of connected back to 5 volts, and there's no voltage potential difference between 5 and 5, so the LED is off. So in order for this OR gate to work, essentially, this transistor has to be on. And that transistor is actually normally on, right? Because we've got this connected right to 5 volts. So we've got current flowing, from the base to the emitter.
Hang on a second. So are you now telling us that if A and B are low in your AND gate that you just demonstrated, that the point here will be high, so we get some base current?
So this will normally be on, unless A and B are on. If A and B are on, then this node here is then going to be connected to ground.
Ah, so you're now contradicting what you said, because you told us before that if A and B are high, this is a logic 1. You drew it on the truth table, but now you're actually correcting, admitting it's actually a logic 0. Aha.
That'll turn off this transistor. So
I think that's all I need to see from that. It really is all I need to see from that one. So how does he actually build the NAND and the NOR gate?
A and B are on, then this transistor is turned off.
Oh, no, I'll just leave it going. Okay, so these are both on. This is turned off. Why is it turned off? Because the output here is low. You told it was an AND gate, my friend, and now you're telling us it isn't? Uh-huh.
And if this transistor is turned off, then this OR gate essentially doesn't work.
That'll do then. So if you go through the last of this video, you'll find he actually then goes to say that you can build the other gates NAND and NOR, the ones that he
gates that you
ignored.
can build with transistors, and here's actually kind of a whole list of different ones. So we saw, the AND gate, the OR gate. We just saw the XOR gate, and we were of course looking at the inverter here. There's also you can make a buffer. I guess this is actually kind of the first thing we made with the transistor, which is the input was on, then the output was on, the input was off, the output was off. Not very exciting, but it can be useful. And there's a couple others that we could also make that we didn't look at.
And why didn't we look at them? Because I'm sure by now you've realised that these two are incorrect. Yeah, that's my take on it anyway. Oh, what am I going to do now, guys? About 2.1 million plus another million people to go and explain why this is all wrong.
Which are the not AND or NAND, the not OR, and the not XOR. Or the
So we still need to build an AND gate and a OR gate. And this is where the fun's going to start. We'll do the OR gate first. An OR gate is actually a fairly simple thing to build. So let's just do it. So we will have, again, 2 transistors. Just draw them so it makes the diagram easy to draw. We have our 2 transistors. We have our base resistor. This is input A. This is 5 volts. Then we have input B with a base resistor. And then we have from here an LED with its resistor. Don't forget the resistor, otherwise it will burn up the LED. Okay, so LED plus its 120 ohm resistor to ground. And then we take the output from this transistor and we also connect it to here. So both the emitters are connected together. Looks a little bit messy, but I'm sure you can see exactly where it's going to go. There, okay. So that now is our OR gate. The output is here. Y. And I'm fairly sure you can see now that if we put 5 volts on either of these, one or other of the transistors will turn on and put the 5 volts through to here, which is the output, and it will light up the LED. If we put 5 volts on both, they'll both turn on, it'll put 5 volts on there and light the LED. So that should make an OR gate that actually works. Let's have a look. I built the circuit here. There, okay. I actually made it slightly different. I put the LED the other side of the resistor, but it doesn't make any difference. If I'll draw the diagram the other way for you, just to show you it doesn't matter which side of the LED the resistor goes to. Ground. This is ground. This is 5 volts coming in. These are the 2 resistors connecting to the 2 bases of the transistors, and both the collectors there are connecting to 5 volts. Let's try it. Let's see if it works. Once again, power on, and we won't bother with the 10k resistors because we know now what that actually does or doesn't do. Okay, so input, the sort of 0, we know about it now. Input, so both inputs are 0, okay, and the output, which is this end of the LED, is 0. Okay, let's put 5 volts on one of the inputs. Okay, so what we have now, we have 0 on this one, we have 5 on this one, and the output is 4.25. So let's start making a note of these. We'll make the same, in fact we'll put them on both because it's just easier. So we now have them on both. Okay, We now know there's 5 volts on both inputs. It's connected directly to 5 volts. Don't even need to measure it. And the output is 4.3. And then the last is input only B with the 5 volts on. And the output now, I'm sure we know because the LED is still lit, is going to be about 4.3. Let's look at this truth table. There is our circuit. As I mentioned, I actually wired it slightly different. I'll just show you to prove it is actually the same thing. So what I actually did from here, I connected the LED and then the resistor to ground. This is out. But that is exactly the same as connecting the resistor and then the LED to ground. The current flows exactly the same in both instances. It doesn't matter which one it flows through first. The LED will still light up. Okay, and these are the voltages we have. So basically, when both inputs were 0 volts, the output was 0 volts. So, truth table. Low, low, Y is low. Okay. Either of them high, doesn't matter which one, high, low, high, or all of them high, both of them high, the output is high. And that is a OR gate. And that works. I said this is where the fun started, didn't I? Well, actually, the fun really starts when we come to the AND gate. If you Google for a transistor AND gate or AND gate circuit, you will find this one. And this is all over the internet, basically. Yeah, it's all over the web. So, Electronic Stack Exchange, Electronics Hub, 101computing.net. You'll find this in lots and lots of places and on YouTube as well. This site is circuitdigest.com, and this again is the same circuit. So this is showing an AND gate where when both inputs A and B are high, the output is high, otherwise it will be low. And he gives you the components. He's using again just NPN transistors, LED, and so on. So this is the circuit which he builds, and he explains the working of the AND gate. This circuit is a little bit odd to me because it appears that there's no current limiting resistor in the LED, which there must be. So if effectively you connect 5 volts to here and both transistors are on, then there would be nothing to limit the current. So we'll put the resistor in there. I'm sure there's supposed to be one. I can see 3 resistors on the breadboard, so that tells me there are. So there's one on each input. No, there's one there. Very strange to me, but there we go. However, if you look down this and he explains the operation, if you come to the bottom, you'll find one comment. This is from February this year. My son and I built this gate, exactly the same materials. And we've built the same AND gate circuit using other tutorials as well, and every time we build it, it doesn't work. Okay, so in case 2, one button is pressed, the light is not, and the other button is not pressed, and the light is still on. And the reason he has that, and he's asking if he has any insight as to why this is happening, is because this circuit doesn't work. Okay, this circuit doesn't work. I built it. I've tested. I'm going to show you why it doesn't work, and then explain why it doesn't work. So here, in fact, is the circuit. I'll just mention that in this section, we're going to look at this circuit, and just before we do, really I suggest, guys, watch this. If you do, you will learn a lot about transistors and transistor circuits, and you will understand a lot of the voltages you can see in those circuits, and it will also help you greatly to understand why a faulty transistor circuit isn't working, because this also applies to that as well as this case where it just doesn't work because of its design. Okay, so this is the circuit. So we have Q1, the first transistor, connected to 5 volts. The base goes to the resistor, and the emitter comes down to the collector of the second one. Again, the base goes to the resistor, so this is input A, input B, and then the output from the emitter through the current limiting resistor and the LED. Okay, that is the circuit. Let me show you why it doesn't work. So the first thing we're going to do is start off with the 0 on both inputs, or not connected. This no doubt is going to create, again, those rather odd floating voltages, but let's have a look to see what it does. So we'll switch on, and now we can check what we have. On the first base then, our rather strange negative voltage. On the second base, the strange negative voltage. So the collector of the first one has 5 volts, and the actual base has a negative voltage. So on the emitter, you would expect this transistor to be switched off because there's a negative voltage for start on the base. Let's see what we've got. Well, in fact, it is off. Yeah, we got practically 0. So the base of the second transistor, the negative voltage, and the output is really negative. So this really doesn't give us any sort of sensible results without putting the pull down resistors. Let's do that. And there we have it. So let's see what voltage we now have on the input. So A is now 0, B is now 0, the base is 0, 0, and then the emitter of this transistor, Q2, the output, is 0.47 of volt. So that is effectively less than 0.8, so we can call that a low. Let me make a note of the voltages. Now let's put 5 volts on the first input A. Okay, we now have 5 volts on A. And just check that. Put the meter where you can see it. 5 volts on A. So the base actually has 4.56. Okay. And the emitter 5.67. So I'll just make a note of those. 4.56, 5.67. And let's have a look at what's going around on Q2. So there's nothing on the input B, so the base should be 0, which it is, and the emitter, the output, has got 0.5 of a volt on, so it's low. So we have the condition 5 volts on A, 0 on B, and the output is 0.5 volts. So that's A is high, B is low, output is low. So that's what you expect from an AND gate. Let's now put the input onto B. Okay. And look what happens, the LED comes on. Yeah, so we can go back onto A, and the input is still 0. On the base, we have 0, okay? So there's nothing on the base of Q1. So I'll just make a note of this. We know there's 5 volts on the collector coming in, because it's connected to 5 volts. What's on the emitter? Well, it has 2 volts on it, on the emitter of Q1. 2 volts. So on the base of Q2, well, we're having the 5 volts coming in on B. So this should have, well, it's got 2.78 volts on it. And we can look on the emitter. And we have 2.07. So in this instance, we have 0 on A, 5 volts on B, and we have 2 volts. 2.07 volts on the output. That LED should be off, should be 0, yeah, if it's an AND gate. Let's now put 5 volts on A as well. So we'll take another little lead. Now connect the 5 volts to A. One moment. Well, you see straight away the LED actually goes brighter. So it was on before, but it wasn't on brightly. Sorry, I knocked the other one off. One moment. That's with both on. So now inputs A and B are high, and we can look on the base. So the first one has 4.5 volts, and the other one has 4.4 volts. Let's make a note of those. Okay, and let's look at the output voltage. So the output voltage now on the emitter is 3.74. Okay, let's look at that on paper. And I apologise for my new webcam that keeps freezing. I've just tried in a different USB port, see if it's any better. Okay, so let's see what we have going on with our circuit in this weird condition. Yeah. So we have 5 volts coming in, going to the collector of the first transistor. Here's the second transistor. LED. Ground. Okay. And the base resistors. Yes, I put the 10Ks to ground, but it's not relevant to this discussion. So we have 0 volts on here, and we have 5 volts on here, and the LED is coming on dim. That's what's actually happening. But this transistor is off, so the LED should be off. Yeah, can we agree the LED should be off? So we measured the voltages. So we know on the collector we have 5 volts. We definitely have 5 volts here. On the base of the first one, we had 0 volts. Okay, so we measured 0 volts here. And on the emitter, we measured 2 volts. Okay, so 5 volts on the collector, 0 on the base, and 2 volts on the emitter. And this is an NPN transistor. And to turn this transistor on, you need to have the base at a higher voltage than the emitter by about 0.6, 0.7 of a volt, and it will turn on. But there's current coming through here, yeah? There's current coming through because you've got 2 volts here, so voltage is getting through it, so current must be flowing. Why? Let's look at the second transistor. So on this one, on the base, we had 2.78 volts. On the base, 5 volts coming in. And on the emitter, we had 2.07 volts. And the LED was on dim. So, a couple of things here. First of all, yes, the transistor is switched on. We've actually got slightly more voltage here than we had here, but maybe that was just the reading, maybe it wasn't, maybe that is what we actually have. And obviously the LED is on because there's 2.07 volts here. Where's the voltage coming from? Well, I'll tell you where it ain't coming from. Yeah, it ain't coming through this transistor. When I built this circuit and I found it was behaving in this way, I then took this transistor out, Q1, and removed it, tested it. Is it leaking? No. I replaced it with another one. Anyway, what happened? It was exactly the same. So I then thought maybe it's some problem where I haven't cut some tracks here, so I used my meter and tested everything. It's fine. But not to be deterred, I then built another one. And you'll see these transistors are actually mounted the other way round. That's because they're a different type. So these are all BC337, and this is a S8050, another general purpose NPN transistor. And it just happens to have a different pin out, so that's why they're the other way round. So I built this one, and guess what happened? It does exactly the same. So there's something that's causing this transistor effectively to feed 2 volts to the LED. Right. I'll tell you where it's coming from. This transistor is off because the base is lower than the emitter. So that transistor is off. That is off. So what have we got now? Well, we've got Q2 resistor into the base. The collector is going nowhere. It's not connected to anything. You can take this transistor out of circuit because I've tried it. It'll do exactly the same thing. That collector is going nowhere. Well, I say exactly the same thing. It'll do exactly the same thing with 5 volts on here, because obviously you can't put 0 volts on there if the transistor isn't there. Okay, that's just being pedantic. But I'm a pedant at times. So LED ground, 5 volts, 2.78 volts. 2 volts on something that's not connected to anything, and 2.07. Well, there's only one place the voltage can be coming from, and that's from the base. That's the highest voltage. And it's actually slightly higher here than there. You know, when you take an NPN transistor and you put it on your multimeter, and basically in diode test mode it looks like you have 2 diodes like that, yeah? Well, that's what you really do have, effectively. When you put 2.7 volts on this end of this diode, it is forward biased. The current will flow through here. Your meter, it will drop some voltage, yeah? Whatever your meter on diode mode said the voltage drop was, 0.7 of a volt. And on the other end of it, you'll have the lower voltage. And the same here. That's where the voltage is coming from. It's the base current in this transistor. Remember, transistor, you pass a small current through the base, and that causes a larger current to flow through the collector emitter. In this case, I measured it. The current is about 3 milliamps, the base emitter current, and that is enough to light the LED up dimly. When we put 5 volts on here as well and switch this on, this now does switch on and lights up brightly, and the current is just limited by that. 120 ohms. When it's being fed from the base, it's limited by that plus this resistor in series, 1k. So you're effectively powering the LED via 1k, via a diode, via the LED, and via a 120 ohm. That's the circuit that you've made. That's why this doesn't work. It does not work, yeah. And that's answered that guy's question from February. Maybe I should go back and tell him. But the strange thing is, this circuit is everywhere. Now, I will tell you guys, I didn't initially figure out what the problem was here and why this transistor was apparently leaking current. So I posted this up on Epilogue forum asking about it, and a couple of 3 nice guys there didn't tell me what the answer was. They just gave me a couple of clues about. The first clue was that effectively the transistor is like 2 diodes and one is forward biased, and I went back with this diagram, 5 volts, 2 volts, 0 volts, and said, well, which one's forward biased? They're both reverse biased, 5 to 0, 2 to 0. And so he said, have a look at Q2. And when I looked at Q2, I suddenly realised that it was forward biased. So thank you to the guys there on Epilogue. Thank you for not actually telling me the answer, but just pointing me in the direction, because it was very satisfying to realise what the problem was. And I will credit you guys at the end titles of this video, so everybody knows who you are, yeah? Pat on the back to you. So, we've learned something really useful here, yeah? The base current is enough to light the LED. What this also should tell you, and this is also important, in any circuit, nothing to do necessarily with logic, in an analog circuit, if you've got a circuit something like this, 0 volts plus volts, yeah, and you've got some voltage on the base, and you've got an open circuit collector resistor, you will see whatever voltage is on the base minus 0.6 or 0.7 here, yeah, base minus 0.6, shall we say, and you will see the same voltage practically here, base minus 0.6 volts. So because you can see a voltage on the collector, you're going to think, well, the resistor's okay, there's voltage getting there. You know, unless you measure the resistor and you realise it's open circuit, but you probably just assume the resistor's okay. It ain't. So just remember that one, guys. How do we make the AND circuit work? I'll tell you how we make it work. And this is probably where the error came from. If you do this, same thing, and use N-channel MOSFETs, okay, doesn't matter which side of the LED the resistor goes, 0 volts, 5 volts, yeah, A, B. If you make the circuit like that, and excuse me not drawing the symbols fully for the N-channel MOSFETs, if you make your circuit like that, it'll work. As expected, it'll work because in a MOSFET there is no current flow between the gate and drain or the gate and source. There is no current. So that's how you actually make the circuit. That works. Yeah. That doesn't. Have I got a red pen? Close enough. Okay. I'll just mention about OR gates something else. So you can actually make an OR or a NOR gate just using one transistor. So we can have a circuit like this. 5 volts. We'll put our LED in so we can see what it's doing. Resistor to 0 volts. We can take output here, Y. And then we can actually connect 2 diodes. Like so. Okay. And these are A and B. So we need to put the resistor in, of course, which could be there, but it could be in each of these. So basically now, if A is high, 5 volts, this diode will conduct and turn the transistor on. If this one is high, 5 volts, this diode will conduct and turn the transistor on. So that is an OR gate. The reason for the 2 diodes is quite obvious, I'm hoping, is that if you didn't have the 2 diodes, you would have A and B shorted to each other. So 5 volts on A would also appear on B and vice versa, and I'm pretty sure that's not what you're intending to do. So you can do that. And to be quite honest, in some cases you can implement an OR gate basically by using 2 diodes. So as a good example, it's not really a logic circuit, but you can have something like this, and you'll see this quite commonly in laptops and on motherboards. Another one here. 2 diodes connected together. Load. SIO chip usually. Okay. Battery. Your CMOS. And 3 volt standby. Okay. So what happens here? It's normally 3.3 volts actually. And your battery is normally about 3.1 volts. So when there's nothing on here, this diode doesn't conduct. Okay, this diode conducts, so you get a voltage on your load, powered by the CMOS battery. When this voltage is here, this diode conducts, and you get an output on your load, your SIO. But because this voltage here is slightly higher than this voltage here, and the voltage drop of the diodes is the same, what you'll end up with is the voltage here will be about 0.2 volts higher than voltage coming in from here. So this diode, when the power is on here, is reverse biased, so your battery is no longer sending any current. But basically, it's like an OR gate. This one or this one can provide power to the load. When they're both high, well, just because of this slight difference in voltage, effectively, that stops supplying current. So that's, you can do that, and you can do similar things in circuits where you make like an OR functionality just using two diodes. The last one we need to look at then is the exclusive OR. There are a number of different ways you can do this. In fact, there's a number of different ways you can do all of these circuits. But this is an exclusive OR using 4 transistors, which is probably the one with the least. I believe there's one with 2, but there are some caveats. Yeah. So this uses 4 transistors. So let's have a look at it. So with this one, we have 5 volts. We have a resistor. I use 120 ohm. And then this goes to 2 transistors. And the transistors are wired as an OR gate. Okay, so we have one of them here, and we have another one. Okay, and there's our 2 transistors. We'll just connect down from this emitter to the other emitter, and from here we'll put our LED to ground, and this is our out Y. So basically this is your current limiting resistor. When we turn this transistor on, it conducts and the LED lights up. When we turn this transistor on, it conducts and the LED lights up. But if we turn them both on, they both conduct and the LED lights up, and that's not what we want to do with an exclusive OR. When they're both on, we want it to go off. So the way we do that is also quite elegant. So we have here two transistors, NPN again, and these are connecting from this point to ground. Okay, we have the input resistors 1K, 1K, A, B, and then these transistors we connect to these. So this base will connect another 1K resistor to A, yeah, and the other one will connect another 1K resistor to B. So that is our circuit. If we look at the way this circuit operates, when there's no input on A or B, so A and B are both 0. There's 0 volts on the base here, 0 volts on the base here, so no current could conduct. So the output would be 0. Okay. If we put 5 volts in here, then this transistor turns on and this transistor turns on. This one via the 120 ohm resistor powers the LED, and the LED comes on. So in this case, A is high, B is low, and the output is high. Ones or H's. Okay, I'm mixing the H's and ones and O's and L's completely now. Yeah, it's getting late in the day. If we take the 5 volts off here and put it on here, this transistor switches on and this one switches on. Again, this transistor lights the LED current via this resistor, so the output is high. This transistor is on, but this one is off, so no current can flow that way. On the previous example, they were both off, so no current can flow that way. So these are effectively not doing anything. So we now have a low or a 0 on A, we have a high on B, and the output is high. 0 low. Okay. If we put 5 volts on both of these transistors turn on, and they connect this point to ground. So these two transistors have now got no voltage supply. So regardless if they could be turned on or turned off, there's no voltage to the LED, so the LED goes off. So high equals low, and that's it. XOR. Yeah. There's only one thing with this circuit, and I'll just show you and explain how you can actually fix it. But let me actually just prove the way this works. So here is the circuit. I've put the 10k resistors in again on the basis to stop them from floating. So with no input, the output on the LED is 0.5. That's a low, okay? If we put 5 volts onto one of the inputs, the LED now comes on, and if we look, we actually have the 2 volts supply on it. Let's get my probe in where we can get to it. 2 volts, okay? If we put the 5 volts on the other input, again the LED is on, and we have 2 volts on the LED. If we put 5 volts on both inputs, the LED goes out, and we have 0.1 of a volt. So the circuit works. The only proviso being that the output is only about 2 volts, not a proper logic 1. But if you wanted to build this circuit and make it actually give you a proper logic 1, what you would do is you would put another resistor in here and make it higher than the value of that one, okay, because it's going to act as a voltage divider. So if we put another couple hundred ohms in here, yeah, 470, something like that, you'll find now the voltage here is more than 2.5 volts. We know from the previous problem on the circuit that when we were feeding the LED through 1k plus 120 ohms, it lit up dim. If we fed it through something like 120 plus 470, it would be brighter than that. So that would actually work if you actually wanted to demonstrate it with an LED and get an output voltage. We can actually work out basically what it is. But it's roughly 1/3 to 4 times 120 is 180. So your voltage here is going to be 3 to 4 volts, something like that. Certainly more than 2.5. Well guys, that was quite long, but I did cover a lot of things in there. I was fighting a lot of disinformation that's available on the internet. I thought all these social medias and such like were supposed to be doing something about disinformation, but nobody seems to care that there are millions of people who now are thanking authors for teaching them how not to make logic gates and how these transistor circuits don't work. But hey, you know, I'm just a little learning electronics repair channel. I don't think I have any chance whatsoever to really educate all those millions of people, which is a shame, but you guys, I'm sure, have learnt quite a lot. I hope you stuck with it through to the end, because we had a very in-depth discussion and look at transistor circuits as well as just logic circuits, and I'm sure that will help you in your fault finding. In the third and final part, we'll have a look at logic ICs, the common families, the 7400 and onwards family of TTL logic, the 4000 series of CMOS logic. We'll have a good look at pull-up and pull-down resistors and the types of output we find on logic ICs, open collector, open drain, what they mean, especially what they mean in circuit and how they can cause faults to occur. We'll also have a look at comparators and how we can use comparators together with logic circuits, transistor or otherwise, to make effectively logic that will respond to certain voltage levels. So all that's to come in the third part. I'd just like to sum up the thing I just mentioned. at the end title credits of this video, you'll just mention a quick shout out to the guys on Epilogue who helped me with that AND gate circuit and to understand what was happening with it. So you guys are going to get a quick shout out. All right. I hope you enjoyed that learning electronics repair video. I hope to see you all soon on another one. And ciao for now, guys.